In these last few lectures, we were considering natural convection due to a heated object placed in a cold fluid. And in that case, the characteristic velocity is not an imposed velocity as in the case of forced convection, but the velocity is determined from a balance between the buoyancy force and the buoyancy force density and the inertial or viscous force density in the momentum conservation equation. And based upon these, we had evaluated what is the characteristic force density, characteristic velocity. If you have an object with temperature T naught in a fluid with temperature T infinity far away, that characteristic velocity is given by g beta times T naught minus T infinity times the characteristic length, where g is the gravitational acceleration, beta is the thermal expansion coefficient. Okay. And the Reynolds number based upon this characteristic velocity is the Grashof number to the half power. Okay. The Grashof number is the square of the Reynolds number based upon this characteristic velocity. In normal situations, the Grashof number is very large, and therefore inertial terms are large compared to viscous terms in the momentum conservation equation. If we neglect viscous terms altogether, we cannot satisfy the boundary condition, and therefore we have to postulate the presence of a boundary layer within which inertial and viscous terms in the conservation equation are comparable. And the boundary layer thickness scales as Grashof number to the minus 1/4 power. Okay. So, scaling the cross stream coordinate locally. Okay. So, in case that the boundary layer thickness is small compared to the characteristic dimension, then we can use a local coordinate system where the streamwise coordinate is along the surface and the cross stream coordinate is perpendicular to the surface, provided the thickness of this layer is much smaller than the radius of curvature of the surface. It can be considered locally flat. And in this coordinate system, we can analyze what is the heat flux from the surface. Okay. So, we had scaled the equations with this boundary layer thickness, and the conservation equations that we had got in the end last time, if you recall, where z is the coordinate that is scaled by the boundary layer thickness, okay, the cross stream coordinate. Vz also scales as delta, because from the mass conservation equation, partial Vx by partial x is comparable to partial Vz by partial z. And delta is the boundary layer thickness, which goes as Grashof number to the minus 1/4 power. And once we scale the variables this way, the mass conservation equation is just partial Vx by partial x plus partial Vz by partial z is equal to 0. It contains no parameters. The streamwise momentum conservation equation, because delta star square times Grashof to the half is 1, the Grashof number no longer appears in the scaled momentum conservation equation, where streamwise diffusion has been neglected, okay, in comparison to cross stream diffusion. The cross stream momentum equation, the pressure gradient is 0. Okay. And the energy balance equation for the fluid temperature, it contains one parameter, the Prandtl number, and the boundary conditions are T star is equal to 0 for z going to infinity far away from the surface, T star is equal to 1 at the surface. That again contains no parameters. Therefore, the solution for the temperature field can depend only upon the parameter, the Prandtl number at a given location. Okay. The solution can depend only upon the Prandtl number, okay, at that particular location locally. The average flux is obtained by integrating this over the entire surface, and since the solution depends only on Prandtl number, the average flux can depend only upon the Prandtl number and the geometry. Okay, so that is the only dependence for the average flux. And therefore, the Nusselt number just simply scales as 1 over the boundary layer thickness times some function of the Prandtl number, some constant that depends upon the Prandtl number. Since the boundary layer thickness is Grashof number to the minus 1/4 power, the Nusselt number is proportional to Grashof number to the plus 1/4 power. Okay. So that gives us the Nusselt number correlation for natural convection. Okay. It is equal to some constant. That constant could depend on the Prandtl number. So, it depends on is some constant times Grashof number to the 1/4 power, okay, for natural convection. Okay. So, then we had considered different limits. One is where the Prandtl number is small, and the second limit, which we have not yet considered, is where the Prandtl number is large. Okay. So, first is the limit where the Prandtl number is small compared to 1. Okay. In that case, if the Prandtl number is small compared to 1, this implies that the kinematic viscosity by the thermal diffusivity is small compared to 1. Okay. Note that the kinematic viscosity is momentum diffusion coefficient, and the thermal diffusivity is the thermal diffusion coefficient. So, this implies that momentum diffusion is slow compared to thermal diffusion. Momentum and thermal diffusion are in the streamwise, in the cross stream direction, and there is convection in the streamwise direction. So, if the Prandtl number and the Grashof number are small, momentum or energy that is diffusing out from the surface is rapidly convected downstream, and therefore, it is restricted to a thin region close to the surface. When momentum diffusivity is much smaller than the thermal diffusivity, the effect of momentum diffusion is restricted to a thin region, which is much smaller than the thickness of the region over which the temperature varies. Okay. Therefore, in the energy balance equation, we had scaled our equation by a thermal boundary layer thickness, determined that thickness from the condition that energy convection and diffusion are comparable in the thermal boundary layer equation. Okay. And that requires that this parameter delta star, that the thermal boundary layer thickness has to be determined from this condition, that alpha infinity by the, that is 1 over the Peclet number times delta T square has to be order 1. And this gives us a condition for the thermal boundary layer thickness. Delta T star is 1 over the Prandtl number, 1 over the Grashof number to the half, whole square root, or this is equal to PR power minus half times GR power minus 1/4. Okay. So, that is the equation for the thermal boundary layer thickness. Now, the solution for the energy equation does not contain any parameters, because we have already made the coefficient of the thermal diffusion term equal to 1 by our choice of the boundary layer thickness. And therefore, the heat flux also does not contain any parameters. The local heat flux does not contain any parameters. The average heat flux depends only upon geometry, and the Nusselt number goes as 1 over the boundary layer thickness, which is PR power half times the Grashof number to the 1/4 power. So, that is in the limit where the Prandtl number is small compared to 1. Okay. The other limit that we were considering was the high Prandtl number limit. Okay. Prandtl number is the ratio of momentum diffusion and thermal diffusion. In the limit of high Prandtl number, momentum diffusion is fast compared to thermal diffusion, and therefore, in the limit of high Grashof number and high Prandtl number, you would expect the fluid velocity field, the boundary layer thickness for the fluid velocity field, to be much larger than the boundary layer thickness. Okay. This is the velocity Vx, okay, and this will be the boundary layer thickness, okay, delta V for the velocity field. Okay. This one you would expect to be much larger than the boundary layer thickness for the thermal boundary layer, okay, which decays over a distance comparable to the thermal boundary layer thickness delta T. Both of these scaled by the characteristic dimension of the object. Okay. So, you would expect the thermal boundary layer thickness to be much smaller than the momentum boundary layer thickness. Okay. And the thermal boundary layer thickness will become smaller and smaller in comparison to the momentum boundary layer thickness in the limit as the Prandtl number becomes larger and larger. Okay. As the Prandtl number becomes larger and larger, the temperature disturbance is restricted to a thinner and thinner region close to the surface in comparison to the momentum boundary layer. Okay. The characteristic velocity is the velocity scale which is comparable to the maximum velocity. Okay. Since the momentum boundary layer since the thermal boundary layer thickness is very small, the velocity within the thermal boundary layer, okay, could be much smaller than the velocity than the characteristic velocity, okay, because the temperature disturbance is restricted to a very thin region. Okay. Therefore, the momentum disturbance in the thermal boundary layer, the velocity, the average velocity in the thermal boundary layer could be much smaller than the characteristic velocity. Okay. And as the Prandtl number becomes large, we expect the thermal boundary layer thickness to become smaller and smaller comparison to the momentum boundary layer thickness. And if there is a no slip condition at the surface, okay, the fluid velocity has to decrease to 0 at the surface. Therefore, it will be small compared to the characteristic velocity close to the surface. Okay. So, that means that the velocity, the convective velocity close to the surface is going to be small compared to the characteristic velocity, which is outside of the thermal boundary layer. Okay. The maximum of the velocity field is outside of the thermal boundary layer, because momentum diffusion is rapid in comparison to thermal diffusion. That means that within the thermal boundary layer, we have to express the scaled velocity, okay, Vx star, okay, as equal to, okay, this Prandtl number to the some power, okay, times Vx double dagger, okay, where Vx double dagger is an order 1 quantity. Note that Vx star is small compared to 1 within the thermal boundary layer. Okay, Vx star scaled by the characteristic velocity, the velocity in the x direction in this thermal boundary layer region, okay, scaled by the characteristic velocity is small compared to 1. Okay. That means that it can be expressed and it goes to 0 in the limit as the Prandtl number goes to infinity. Okay. It goes to 0 in the limit as the Prandtl number goes to infinity. That means the velocity in this region can be expressed as some power, negative power of the Prandtl number, where q is not yet known, times this quantity Vx, okay, which is an order 1 quantity. So, this Vx double dagger is an order 1 quantity within this region. Okay. So, therefore, since the velocity is 0 at the surface, the velocity has to be close to 0 within the thermal boundary layer, and the magnitude of the velocity will decrease as the Prandtl number increases, or the ratio of the thermal and momentum boundary layer decreases. Therefore, we have postulated that it is equal to some power of the Prandtl number, a negative power which goes to 0 as Pr goes to infinity, times an order 1 quantity which is Vx double dagger. Okay. And we will scale the z coordinate, okay, is equal to z by Lc times the thermal boundary layer thickness. Okay. From the mass conservation equation, okay, Vz star is equal to Vz double dagger into, okay, Prandtl number per minus q. Okay. Okay. Or let me just back up. Okay. We require that within this boundary layer region, partial Vx star by partial x star plus partial Vz double dagger by partial z double dagger has to be equal to 0. And since Vx star goes as PR power minus q, we require the scaling for Vz is equal to PR power minus q, okay, times delta t. Okay, so times Vz double dagger. Okay. So, that is the scaling for the z velocity. Okay. And let us substitute these into the momentum and energy equations. Okay. If we substitute these into the momentum and energy equations, okay, the momentum equation first. Okay. If you recall, it was Vx star partial t by partial x plus Vz star partial t by partial z. Okay. I will neglect okay, this is equal to 1 by Prandtl number Grashof number power half into partial square t by partial x square plus partial square t by partial z square, okay, where z star is z by Lc and Vz star is Vz by Lc. Substituting these parameters here, Vx star is smaller, sorry, Vx double dagger is smaller than Vx star by a factor of PR power minus q, okay, and x star is scaled by Lc. So, I will just get PR power minus q into Vx neglecting streamwise diffusion in comparison to cross stream diffusion once again. And in the case of cross stream diffusion, the boundary layer thickness is delta t smaller, okay, than the characteristic size. Okay. So, that is the momentum conservation equation. Okay. I am sorry, that is the thermal energy conservation equation. Okay. Similarly, I can also write an equation for the streamwise momentum conservation. Okay. Equation for the streamwise momentum conservation, if you recall, partial Vx sorry, Vx. Neglecting once again streamwise diffusion in comparison to cross stream diffusion. Therefore, I do not have the second derivative with respect to x in the viscous term here. Okay. And substituting for Vx star once again, okay, using this expression, okay, substituting for Vx star once again using this expression, okay, you can see that you will get the Prandtl number to the minus 2q, okay, into Vx double dagger partial Vx double dagger by partial x plus Vz Okay, so, those are the two equations. Okay. Note that the momentum boundary layer thickness is much larger than the thermal boundary layer thickness. Okay. So, over a distance comparable to the thermal boundary layer thickness, you would expect momentum diffusion to be much larger than momentum convection. Okay. Over a distance comparable to the momentum boundary layer thickness, there is a balance between momentum convection and momentum diffusion. For lengths much smaller than that, okay, the Reynolds number based upon the thermal boundary layer thickness is small, and therefore you would expect momentum diffusion to be dominant for a smaller length scale. Okay. As the length decreases, diffusion is more important in comparison to convection. That is the reason for small scale flows the Reynolds number is small and it is diffusion dominated, whereas for large Reynolds number, when the length scale is large, it is convection dominated. So, therefore, within the thermal boundary layer thickness, you would expect that there will be a balance between okay, I have neglected plus T star Gx star. Kindly note I have neglected the body force here, that was a mistake. Okay. Kindly include the body force in the formulation. Okay. So, yeah, and also I have to write velocity in terms of Vx double dagger, and therefore I will have a factor of PR per minus Q here. Okay, I will have a factor of PR per minus Q here. Okay. When I express Vx star in terms of Vx double dagger. Okay. So, over a distance comparable to the boundary layer thickness, you would expect momentum diffusion to be much larger than momentum convection, because they are comparable over the momentum boundary layer thickness, which is much larger. Okay. That means that there has to be a balance between these terms here. Okay. In the momentum equation, the diffusion term and the body force term over a thickness which is much smaller than the momentum boundary layer thickness. Okay. And from that, you can easily see that from this, the if this is comparable to the body force, that means this term has to be order 1. Okay. And therefore, I get the relation delta T square is equal to, okay, PR per minus Q, okay, GR per minus half. Okay. That is the expression for the boundary layer thickness. So, that the coefficient of the viscous term is 1. Okay. So, that is one relation I get for this index Q, okay, by balancing the viscous term with the body force term in the momentum equation. The second relation that I will get is by balancing the inertial and the convective and diffusive term in the energy balance equation. Okay. The second term that I will get is by balancing the convective and the diffusive terms in the energy balance equation. Okay. So, here I would require that PR per minus Q is, okay, 1 by PR GR per half, okay, delta T square. Okay. Or alternatively, delta T square is equal to, okay, PR per 1 minus Q GR per minus half. Okay. Yeah. Okay. If both of these have to be the same, then 1 minus Q has to be equal to minus Q. Okay. If both of these are the same, I am sorry, this is minus of 1 minus Q. Okay. So, if both of these scalings have to be the same, then minus of 1 minus Q is equal to minus Q, which implies that Q is equal to 1 by 2. Okay. Okay. And if q is equal to 1 by 2, we get that delta t star, okay, is equal to PR power minus 1 by 4 GR power minus 1 by 4. Okay. So, that is the relation we get for the boundary layer thickness in this case, okay, where the velocity is small. So, in this case the result shows that for the balance between the momentum diffusion in the momentum conservation equation and the body force, as well as simultaneously a balance between thermal diffusion and thermal convection, the parameter q has to be equal to minus a half, okay, is equal to a half, or the scaled velocity is equal to PR power minus a half, okay, times the goes as PR power minus half, okay, in the limit as the Prandtl number goes to infinity. Okay. So, this is the boundary layer thickness, and if you incorporate this boundary layer thickness, on the left side this minus 2q will be equal to minus 1, okay, in the momentum equation. So, you neglect the inertial terms as is expected in the thermal boundary layer, which is much thinner than the momentum boundary layer, and where momentum diffusion is large compared to momentum convection. Okay. So, that is the boundary layer thickness that you get, okay, by balancing terms in the energy equation as well as the momentum equation, convection and diffusion in the energy equation, the body force and the viscous term in the momentum equation. And if you do that in this limit, you can neglect the inertial terms in the momentum equation, and then the equation is now independent of parameters. Okay. And using the same arguments that I had earlier, qz is equal to minus k into partial t by partial z. Okay. And this is equal to some constant, okay. Okay. So, yeah. So, this is the local flux, and the average flux is equal to 1 over s integral over s of qz, okay, which is equal to and the Nusselt number is equal to q average by k okay, that is the correlation for the Nusselt number. So, this is equal to some constant, okay, in the limit Prandtl number greater than 1 times 1 over delta t star. And delta t star goes as PR power minus 1/4 Grashof number power minus 1/4. So, this is equal to some constant Prandtl number power plus 1/4 Grashof number power plus 1/4. So, this is the Nusselt number correlation in the limit of high Prandtl number. In the limit of low Prandtl number, the Nusselt number correlation is Prandtl number power half times Grashof number power 1/4. So, this completes our discussion of the correlations for natural convection, which I had discussed but had not derived when we did dimensional analysis. For general case, the Grashof number is equal to some function of Prandtl number, some constant that depends on Prandtl number, times Grashof number power 1/4. In the limit of low Prandtl number, it is equal to Prandtl number power half Grashof number power 1/4 times a constant. High Prandtl number is proportional to Prandtl number power 1/4 Grashof number power 1/4 times a constant. So, this is our discussion on natural convection. The analysis the non-dimensionalization of the equations to obtain the dimensionless parameters Grashof and Prandtl numbers, limit of high Prandtl number, limit of high Grashof number, scaling the equations by a boundary layer thickness because diffusion is neglected to a thin region near the surface, and we get the Nusselt number correlation as a function, some constant which depends on Prandtl number times Grashof number to the power 1/4, and the two special cases for high Prandtl number and for low Prandtl number. So, this completes our discussion on natural convection. Qualitative discussion, but we managed to get the forms of the correlations. So, this I will complete this section on natural convection. Thank you.